warahmatullahi wabarakatuh. My name is Surya Fitrah binti Amran from Group 4. In this video, I will present 3 operational amplifier configuration: the inverting amplifier, non-inverting amplifier, and the summing amplifier.
My name is Nur Adrana Najwa binti Syarah Anwar from Group 4. In this video, I will present 2 operational amplifier configuration: the differentiator and integrator amplifier.
The objective of this lab is to understand the behavior of op-amp circuit, compare the theoretical gain with the simulated output, and observe the non-ideal effects such as clipping and saturation. Through this presentation, I will show the LT-SPICE simulation result and explain the key principle behind each configuration. For the first circuit, which is the inverter amplifier, I use R1 or resistor 1 kilo ohm and R2 33 kilo ohm with the 1 volt peak in at the 1 kilohertz. The theoretical gain is negative 33. In the simulation, the output waveform is inverted by 118 degree and the amplitude is slightly lower than the theoretical value. The waveform is also clipped because the calculated output exceeds the supply voltage of 15 volt, causing the op-amp to saturate. In experiment, gain is equal 14 and out also 14 volt. For the non-inverting amplifier, I use resistor 1 equal to 1 kilo ohm and resistor 2 equal to 10 kilo ohm. The theoretical gain is equal to 11 and 11 volt. The simulation shows the output remains in phase with the input and the amplitude increase according to the gain. Any small difference from the theoretical value is due to non-ideal characteristic of the op-amp. In experiment, gain and Vout are same with calculation value.
Integrator amplifier. For the circuit, which is an integrator amplifier, I use a RS 100k ohms, RF 10 m ohms, and use a capacitor 0.01 microfarad with 1 volt peak input at a 1 kHz. The theoretical Vout is a negative 1 kV. In the simulation, the output voltage is a 0.845 volts. The waveform for the integrator amplifier convert a square wave to a triangle wave because integration transform constant input into the linear output slope. Differentiator amplifier. For the differentiator amplifier, I use a RS 1k ohm, RF 100k ohm, CS 0.01 microfarad, and another capacitor 100 picofarad. The theoretical Vout is negative 2 volts. In a simulation, the output voltage is a negative 1.9885 volts. The waveform for the differentiator amplifier transform a triangle wave into a square wave but have a spark because it measures the input slope. The triangle wave constant slope create a square wave constant voltage level.
For the summing amplifier, I use R1 equal to 10 kilo ohm and R2 2 kilo ohm. For the RF equal to 10 kilo ohm with 2 input signal. In calculation, we are equal to 6 volt. The simulation confirms that the output is weighted sum of both input with inversion due to the inverting configuration. The waveform changes according to the combination of the input, and small amplitude reduction can be seen at a higher frequency. In experiment, we are same with calculation value. The difference between the theoretical and simulated result can be explained by 2 main principles. First, output saturation occurs with the calculation output is larger than the supply rails. This explains the clipping in the inverting amplifier. Third, the limit slew rate of the 741 op-amp reduces the output amplifier and cause slightly phase delay in higher frequency. This principle shows why ideal equation and real simulation are not perfectly identical. In conclusion, this lab helps us understand how op-amp circuit behave in both theoretical and simulation. The inverting, non-inverting, integrator, differentiator, and summing amplifier follow the ideal equation, but real op-amps have limitations such as saturation, finite bandwidth, and slew rate. Overall, this lab highlights the importance of differentiation between ideal calculation and practical circuit performance. That's all for me. Thank you for watching.
That's all.